Great, let's get started. Hi, everyone. Welcome to today's session, Incorporating Ontological Information in Knowledge Graph Learning and Applications. I'm Junheng from Microsoft, currently a researcher at Knowledge and Language team in Azure Cognitive Service Research Group. For today's talk, I will introduce mostly from my, mostly in the past during my PhD about my thesis. So more about the work I've done at UCLA. Let's start with some background knowledge on the knowledge graph, and the knowledge graph in my meaning, in my definition, and also the representation learning on knowledge graph. So knowledge graph, as everyone heard from other sessions as well, is ubiquitous for whenever you go search to your favorite artists, singers, or political figures, or even anything when you're learning online, you cannot avoid get access to certain knowledge graph or knowledge base. It has been in various shape or domains. Sometimes you are not even aware of that's a knowledge base or knowledge graph. Most likely people are going to talk about or see Wikipedia style of encyclopedia knowledge graph, but also in other domains like e-commerce as product information, biomedical as pathways, proteins, and biomedical and biological knowledge, and more likely they'll have more academic style for common sense knowledge, or such as word net or concept net. Those are various type of knowledge graph that support various functions. In academia, it's well connected to natural language processing, some tasks like QA or conversational AI. Also, it can be connected to computational biology while using the existing medical knowledge to help propose new drugs or other treatments. In more industrial scenario, for e-commerce, as I mentioned before, the knowledge graph can also be used for personalized recommendation and many others. I think from my observation of multiple sessions about how people are defining a knowledge graph, it really varies a lot. So I think to my session, I'll just starting with claiming the thing that I'm working on in the knowledge graph, the format that we have. So typically a very straightforward format will be some triplets where subject, predicate, and object are in a triple format is connected or kind of consistent with the RDF or RDFS in semantic web communities or other type of well-known ontologies. And also more in a label property graph, such as Wikipedia, where you have an entity page, where you have property modifiers, also other like supplementary information. But in our talk today, most of the KG that I'm referring to in neural-based modeling is actually in a triple format, something like this. So basically, you have a lot of nodes and edges are actually composed with different relations, and everything is described in the triple, which is the simplest way of describing the world knowledge. Definitely, there are some more advanced and also ontology information to make the knowledge graph more unified, more machine readable and understandable, and more easier to infer. So another group of research since 2013 is knowledge graph embedding, which is a kind of a connection to neural-based method where people are actually changing the high-dimensional graph data into a latent vectors and use that vectors for downstream tasks such as similarity search, link prediction, triple verifications, etc. So the general idea is to input such triples and output more like embedding tables where each vector represents a certain entity. This is the high level of knowledge graph embeddings and how the embedding works for many tasks. The way that we optimize to learn this embedding is by designing, in more traditional way, is by designing a certain function, or you call it scoring function. There are at least 100 papers talking about designing the best score functions to make it as inclusive as to include and incorporate multiple properties such as translational or compositional logical inferencing in knowledge graph triples. But generally, there are a certain score function, either translational, bilinear, or other neural networks to define with a score function to represent the plausibility of a certain triplets by input the embedding of the head relation and the tail entity. But I think something is missing here. So as I mentioned, in the knowledge graph embedding communities, people are actually treating the knowledge graph just as plain as triples. However, as I mentioned, there are more rich information about ontologies to represent each entity, such as classes, subclasses, parent classes, as well as other type of domain range and other. The semantic web community would develop things that try to define a unified universal language to better describe what is the schema as well as other type of properties. So that is where the ontology can come into place. Most likely, one of the representative structure will be taxonomy, where defining classes, subclasses, and also the instances are actually the installations of a certain concept. So in that case, that being said, the knowledge graph is more hierarchically structured data format or data source that are not just should be treated as plain embeddings or plain triples. So in that case, we want to ask a question. We still want to keep in the neural-based method, such as knowledge graph embeddings, to do it in a more in the knowledge embedding communities, but also try to incorporate more about the rich semantic structures, such as taxonomies and ontologies, into the learning procedure. And that can better help in understanding the data and better represent the data. So for today's work, I actually organized my thesis work into a knowledge graph itself. But I'm not going to talk about all of the work I've done during a PhD, but mostly I'll focus on the first two work where the knowledge graph encounters some ontological information. For today's agenda, and also the paper that I'm mentioning, publication that I'm mentioning, are I'll listed here. We can later refer to for more information. Let's start with a case. This is a snippet that might cause controversy about how a knowledge graph would look like. This is definitely not a real-world knowledge graph. It is a very simplified version where I try to incorporate some ontology information. So here, the knowledge graph is split into two views. The lower is more like real-world instances. The upperwards is all concepts, or other terminology may determine as classes, subclasses, etc. This is by no means the full complete information. It's just a variant of reformulation of what a knowledge graph could look like based on the two-view formulation by splitting the ontology or classes and the instances. So in this case, when we are trying to, the knowledge graph embedding method want to learn embedding for Barack Obama, it will gather the interactions with the entities that it connects, but also being regulated by the politician or person concept in the ontology upper side. So this is the general, the motivational case that at least for knowledge graph embedding method, we should not treat everything equally as in triples, but also need to incorporate a little bit structure. So this is just to make a simple split in one way, but not necessarily the optimal way. But it does help compared with the traditional method, it does help in terms of learning latent representations. So here's how we do it. So as we mentioned, we kind of make the graph into two parts and as two views, and one is smaller with smaller number of nodes as concepts, and lower part as a larger number of nodes as instances. And the connection is definitely those type links, or the class link, one certain entity belongs to one class. And the horizontal one are actually the same as relational facts, or ontology connections, semantic connections, but the vertical links are actually types that are connecting or grouping certain categories of the entities. So something we do differently is we consider this is a type of regularization. By simply consider those type links or bridging those two views, the very straightforward image for this is we should think about a regularization to more like pushing those entities that belongs to a certain type are closer in the embedding space. We can directly look at the right side of this cross-view transformation, which has a neural layer of transformation defined from the instance embedding space, entity embedding space to the concept. So after this transformation, the transformed embedding in the concept embedding space should be close to its associated types. As for the regular regular relational facts, we just adopt the similar knowledge graph embedding techniques, which some of the representative Bayes or trans-EED smaller whole or other type of scoring functions to continue this training as others. We just add a regularization term for cross-view to regularize the classes as well as its instances. This simple splitting method for a knowledge graph formulation can lead to better performance in triple completion or link completion on Yago and DBP datasets, as well as in entity typing, which given a certain entity, we want to predict what type it is to reduce disambiguation. This example for some long tail entity, if we don't know about the types, for missing information, we can use this embedding method to help navigate the correct type, especially for the names that might be a city name, might be a person name, etc. This type of framework is definitely extendable. So recent research communities are extending this certain taxonomy modeling effort not into a vector embedding like what we have done in the work that I just introduced, but trying to extend it into a box embeddings, for example, which means one simple vector might not even enough for complex taxonomies. So some recent works from my colleagues are actually doing the taxonomy or the locker level in the box embedding space, where the box embeddings is even better for encoding the logical constraints, super or child class neighbors, and also their logical connections. Those are some extendable connections to box embedding based taxonomy or ontologies. We apply a similar idea not just to concept and its entities. Any kind of two views or two domains of knowledge, as long as they can be enhanced with each other or mutually benefits based on their knowledge source, we can actually gather information and try to jointly learn the representation of those embeddings. One example that we have tried is in bioinformatics, we connect the protons to the gene ontology annotations, where we still have the very similar two-view framework to connect the protons to biological process, molecular function, and cellular components annotations. This is also far from the real complexity of what happens in the metabolism in our body, but it's a simplified configuration of protein to its annotation, and to better help predict protein-protein interaction type. We also have some customized modules, such as weighted connection layer, where we connect with two views of knowledge. Their specificity or the fine-grained level of associated annotations should be naturally assigned a stronger weight if the specification is relatively in a lower fine-grained level instead of in very general. So it's more like a conditional recipe for this alignment, or previously we called it regularization of its types. But right now it's not its types, but it's annotation in another knowledge graph. So by adding this information, it helps with PPI, protein-protein interaction prediction, even though we don't actually have a very heavy model for the sequence itself, but it still happens it benefits a lot to have a comparable performance with the PPI prediction. We also identify a case where the SARS-CoV-2 protein, a viral protein called NSFP7, how it can connect to different membrane and cellular component in human bodies. Although it is, I have definitely not sufficient knowledge to identifying whether this is true or not. But from a computational perspective, it will at least bring some insight to biologists who are mostly skeptical about how the computational results, but it still does represent what is the insight bring by machine learning models. The next part of the talk is about still kind of like a specific framed knowledge graph or two-view knowledge graph, but more applied to industrial setting. So here we identify a problem that are well suited for this one, which is a complementary recommendation. So just a quick summary of what is complementary recommendation. It's something like purchase together recommendation. When you put something in the cart, like if you put a pillow in the cart, you wouldn't be very happy to see another 3 pillow popping up into the cart as recommendation list. So in that case, the complementary recommendation is somehow very different and sensitive to know what are the diversified burden, and also should be very different from the similarity-based method. So in this case, how we can approach this diversified by using the sense of knowledge. So here we don't even have a knowledge graph yet. We need to create one, at least a temporary one, for a behavior-based product knowledge graph. The nodes are naturally item itself, like the product, with the features such as categories and types, especially focusing on the types. We will use that later. And also other type of title, description, and even image features. And the edges here, since are behavior-based, we assume that some behaviors like also bought, also view, but after view, those behaviors indicating in customers' preferences or the product's connection, product relationship in a customer browsing session. So in that case, we use that as a weak supervision signal to indicating their substitutes or complements. So then a knowledge graph is ready. Although it might not be the same flavor of the knowledge graph we have in such as Wikipedia, but at least it's a structured knowledge that we are connecting the products with their potential connection, potential relationship between those items. A quick note on the knowledge graph that are previously showed versus the graph that we just created. It's somehow very different, but it's still comparable in various aspects, such as source, their quality, and their relations, whether they are like thousands of relations or kind of manually defined relations, attributes, whether logic rules are applicable or downstream tasks. So at least something is shared here. From the ontology view and instance view to a very naturally transfer to a specific item and item types. So here, as you see, the upper one changed to a product type, generally representing its functionality, and the lower side are generally a very specific item. It still follow the pattern that upper side is relatively small, probably just thousands, but the lower side is definitely in the billion level. So since we have two views, then we should have two levels of modeling, either in types and in specific item. Since we are doing complementary recommendation, the types is a key factor to do the diversification of what you recommend, given a specific query to purchase together. In most cases, the recommendation should not be the same type. So that's why we have a specific dedicated module called type transition modeling, which generally focusing on the effort in the top type level. So there are 3 modules. First one, we have a backbone or backhand to initiate product embedding from the from the product log features. And next is about doing type translation modeling, going up to infer complementary types. And then combining with the complementary types and query item itself, we're coming back to the item level to recommend specific items. So due to the time limitation, I'll just skip some of the details in each module based on how to build a product embeddings and a complementary type, how to, based on the training data, we learn a encoder and decoder style module to learn this type transition to indicate the potential complementary relationship in the item type level. And getting back to the item, combining with the item type and query embeddings, query product embeddings, and they will output a type regulated item prediction. So this is a verification of the demos, how the type are being transit from the query type to its complementary type. And more visually, we can have results that are not from previous code purchase data, but relatively largely make more of the item a qualified recommended item given the specific query item. Even for some code start item, we can use this framework as long as we have the item features to get the initial embeddings and also apply this item type recommendation and item specific recommendation. We can generate a lot of candidates, even for code start items with few customer interactions. We also have some framework on using graph neural network as the encoder for knowledge graph entities for some medical ontology for ontology matching problem. Just a high-level summary about what I've talked about in this session. For neural-based method, I want to have the introductory work that are bridging the knowledge graph and the ontologies communities to make sure they are not exclusive with each other and they can have connections by using the ontological information. The knowledge graph representations are actually better with the help of dedicated modules. And also it is easily applied for many industrial scenarios. For the last couple of minutes, this was not originally planned when I signed up for this session. I just want to add some few slides to talk about what it means when the new player, a large language model, joining in the knowledge graph conversation. It has been a long story that knowledge graph has been used, including not only just whether ontology level, whatever structure has been planted or plugged into language transformer style models to make the model more factual and also serving as fine-tuning or pre-training task in papers such as ERNIE or other type of knowledge augmented method. With the emerging language models, we still consider a knowledge graph as a unique tool because of its unique nature, the clarity it delivers to the human beings, and also the factuality is one of the key reasons that rejecting a large language model on hallucination and many other tasks. As a knowledge graph communities, we might not like the large language model to generate creative works. We're focusing more on factuality. So this is just a snapshot example that given if you want to read a paper talking about how the SARS-CoV-2 or protein can be a treatment, but rather in the graph, it conveys a very clear idea. Even for biology freshman as myself, I can still get what is the key factor that playing the role. As the last slides here in my session, I want to point out whatever the information that such as ontology or specific knowledge graph, the large language model are actually can play some new roles. To first can have the initial knowledge graph construction fully automated by large language model, or knowledge graph as a large language model plugin or two-former idea to help retrieve real-time answers, fact check, or reducing hallucination. It also connects to enterprise knowledge graph such as Employee Central about project organization, etc., to help with personalized recommendation. And also, the last one I would point out is whether the structured knowledge graph input and output can be inside of a prompt engineering into a knowledge graph, into the large language model to further improve the accuracy, the factuality, and coherence with many downstream tasks. I think that's the end of that. Concludes my talk, and I'm happy to take questions. I saw one from Yong talking about the product graph, about the product embedding, consider images and videos. So that part, since the Amazon intern projects I've done in that case, the short answer is images for sure is yes. The videos, I'm not sure whether they should be fully considered. But for image, I think the simplest way is to have an image encoder to concatenate or fused with the other catalog features. So in that case, the module that we in my experiment does not have image embedding, but in possibly in the model variant or later implementation for recommendation, the product images, especially the images with description, like a lot of current product in Amazon might have this pattern to have this description included in images, might also be helpful to understand the product embedding. So I think that's a great part to first have a valid product embedding to start the framework that I mentioned. Another additional question about the, let me just coming back to the slides real quick. So in this work, basically it's manually restricted to whatever number you want to have. So 3, 5, we can limit it to the top 5 most complementary types. And for each complementary type, we have a number of what are the items that we should write. So it's basically 5 types, 10 items each, that will result in 50 items. We can definitely not put all of them together. So in that case, there are some post selection or filtering procedures to select the top 3. The top 3 might still not necessarily this 3 different types based on certain threshold for this post processing. So it's basically like selection and re-rank process. Another way of that is based on a complementary threshold. Then you can possibly have a different number of complementary type. But right now in this work, it is just fixed as 3, the magical lucky number. Thank you, and I don't see there are no coming questions. Yeah, I think that's pretty much the end of the talk. Thank you very much for attending this session. I hope you have a great day and enjoy other sessions later.